it. So this may take probably 45 minutes to an hour. I guess we'll find out together. So we'll see how it goes. If you have questions, raise your hand, ask. Just interrupt probably because I probably won't be able to see you raise your hand. What are we doing here? So within the next hour or so, we're going to do a quick foundational review of the base moments, which may be like, well, why are we going that far back? Well, it's just like in the summer. Like if you don't have the most sound understanding of ZDR, you're not going to understand the ZDR arc very well. And if you don't have the best grasp of KDP, well, then you're not going to have the best grasp of its associated signatures. They're not going to make a whole lot of sense. So we'll rip through ZDR, KDP, and CC and how they relate to Winter, because that'll really be a foundation for what we'll do, which is then go through some of our very key signatures and their conceptual models. We'll apply it, and well, hopefully you'll take at least something with you home. Otherwise, well, I guess I would have failed then. All right. So what can dual-pol do and what can it not do? All right. So we'll start there. So what it can do, well, it can do quite a bit. And kind of one of the reasons why I've kind of put this together and made it an emphasis is that I think a lot of times dual-pol data kind of gets, drops to the floor in the winter, and there's a lot of information that I don't necessarily know how well we're all utilizing. And admittedly, some of these things are not the easiest just right away. So it takes a little bit of unpacking, which is hopefully something that we're gonna do today. So what can dual-pol do is that can spatially depict melting and refreezing patterns and how those are changing in time. And well, that seems pretty important. It can really highlight areas of prolific ice crystal growth aloft. I give you a pretty high confidence of the P types aloft, whether it's a mix or no mix, wet versus dry. Obviously, it can't tell you exactly what's hitting the ground. You're going to have to marry conceptual models and environmental data to the dual-pol data for those below beam effects, which in the end is a shameless plug for staffing a winter meso analysis position. So not just for the summer, there's a heck of a lot of data to go through for the winter to land that forecast. So that's a shameless plug. Also, dual-pol's our most rapidly updating data set you have in your winter mesoanalysis toolbox. That gives you insight into the thermodynamic and hydrometeor microphysical processes. It's updating pretty rapidly and giving you a lot of information. So how well are we all utilizing that data? And another shameless plug for staffing a winter mesoanalysis position. So one thing, we'll start super basic and then we'll ramp up in complexity. One thing that I think folks can tend to struggle with radar is you get caught up in the definitions of some of these parameters and, okay, can we break that down into just physically what it represents? So one thing that we like to teach is just like this one word thing, like when you speak spectrum width, which we're not going to spend a lot of time with here, think chaos. When you see ZDR, think shape. When you see CC, it's similarity. KDP is stuff. I put a turkey on there because I guess turkey and stuffing, there wasn't really a good icon for stuff. So that's what you get. And how shiny is reflectivity. So just breaking it down to these simple physical connections to what these parameters really mean. And then you can really put the pieces all together. So we're going to go through kind of the more foundational ZDR, CC, and KDP, because we really got to make sure that we have a good understanding of what those are if we're going to have a chance of understanding a refreeze signature or prolific ice crystal growth aloft. So let's go. So first one, ZDR. The technical definition is the difference between the horizontal and vertical reflectivity factors. Obviously, we send out a horizontal and vertical pulse, which in the end, the main thing we get out of this is shape, right? For the most part, we live in positive ZDR. Okay, occasionally in the winter with some vertically oriented ice crystals or some radar artifacts associated with some scattering, more so in the summer. But we'll leave that for the summer. We'll live in our very boring winter that we are having right now. And ZDR, largely, we're living in a positive framework, increasing levels of moisture generally corresponds to larger horizontal axis, which gives us something that looks more like an oval compared to a sphere. Although we will talk about spheres and kind of the summertime or the wintertime, version of hail, which is snow aggregates essentially for zero ZDR. Got to remember though, with ZDR, it's biased to the bigger targets in the sample volume. So that's one thing to keep in mind, both from a summer perspective and a winter perspective, is that the larger targets will bias the ZDR. So if you have larger targets that are more spherical, your ZDR will drop down, even though there's potentially more targets in that volume that are a little bit longer horizontally, but they're smaller. So just something to keep in our mind as we go forward. This is on the left there. If you're in the Chanhassen office, the Duluth office, which is home turf for me, or Wilmington, Ohio, your radars are going to be highlighted. So thank you for providing me the weather to show some examples. So here's Chanhassen, pretty clear rain versus snow. So in general, ZDR for rain will generally be larger than ZDR for snow. And that really helps to mark that transition in from rain versus snow for those thermodynamic setups where it's basically that surface-based warm layer. So it's pretty much a rain versus snow outcome. And we can see here, my home turf of the northeast side of the Twin Cities there is under the mix, and Chanhassen, you essentially are under the snow, where we see that much more uniform, much more lower ZDR. That's for snow. And then where we're getting that mix, where we have those partially melting hydrometeors that are a little bit longer on the horizontal axis, we can see pretty closely how snow versus a mix versus probably rain in western Wisconsin, how that pattern is set up across the Twin Cities. The lower the particle density, also the lower the ZDR. So a snowflake is much less dense than a raindrop. And because of that, that's also plays into why ZDR is a lot higher for rain, or a mix of rain, snow, i.e. partially melted snowflakes that are on their way to becoming raindrops. Why that ZDR is a lot higher than it is just for snow itself. Like we talked about, generally snowflakes, they start to melt on the outsides and work inwards. So that leads to positive ZDR values as they begin to look more and more like a hamburger-shaped large melting raindrop to the radar. And as you would expect, just as we would have in the summertime, that leads to very high ZDR in those melting layers. Kind of a little bit next level of ZDR application is zones of dendritic and plate growth. So when these crystal habits start to form aloft, generally they're aligned horizontally. They're kind of fluttering, and they're look pretty flat. They're a lot more horizontal than they are vertical to the radar. It's not just this perfectly falling dendrite. They're kind of fluttering, and so they have ZDR values that are a lot higher. So if we look aloft and we see these higher values of ZDR aloft, that may be associated with dendritic growth, as those fluttering dendrites are first forming in that region. Now, where will ZDR be lower? We'll stick with the same cross-section here. So if we go back a slide, we can see this zone aloft, about 10 to 15,000 feet of higher ZDR aloft. That's associated with, you just have to trust me that it is associated with dendritic growth. But we see that the ZDR actually decreases towards the surface. And the reason for that is all these fluttering snowflakes clump up and they form a snow aggregate. And just like in the summer with hail, these snow aggregates, they look more spherical, they kind of tumble a little bit. And because of that aggregation process, we see ZDR decreasing from the dendritic growth zone towards the surface. And so these snow aggregates really represent pretty prolific snowfall rates. So if we see this signal of higher ZDR aloft that's decreasing towards the surface, that's probably associated with dendrites that are being generated aloft, fluttering with larger horizontal axes. They're starting to then clump up as they fall into these snow aggregates. And because they're clumping and look more spherical to the radar, ZDR decreases towards the surface. There will be we'll chat about KDP associated with this as well. So KDP, probably the most confusing of all the dual pole moments. And it's not truly a moment. It's actually a range derivative of a moment. So sorry about that. There will be f primed of x in this presentation, but it will only be to show you why we care about PDP and not phi. So KDP, when you think KDP, I mean, it's a little bit of a casual definition, but think stuff. It's probably the easiest way to think about it. How much liquid is being run into largely, and then in the winter especially, it may not all be liquid. So just how much stuff is being run into, because that stuff is going to do things to the wave. The technical definition is the range derivative of differential phase. So that's not very helpful. That's why we don't use differential phase. So let's think about this. We send out a wave, right? Horizontal and vertical pulses. And what happens is that as those waves are hitting things, its phases are being shifted. Horizontally targets, so those positive ZDR targets that are more larger horizontal axis, they'll produce more positive phase shifts in the wave. Spherical targets will be near zero. And also, this is where really the stuff comes into play, is that as it's running into more stuff, well, we're going to shift that wave a lot more. So what the radar measures just from a base moment is just differential phase. So it's just saying, as I'm going down the radial, how much is the phase shifting on the wave? That's fine. So in the end, you just get this accumulation of how much the phase is shifted, which is fine. But what we really care about is where is that phase shifting, and especially where is it shifting the most? Well, back to Calc 1, and it's calculus time. So we take the range derivative, which is just saying, hey, where is this wave being shifted the most? Where is it running into the most stuff? Where is it running into the most liquid water, especially from a standpoint of melting or in the summertime and deep convective processes. So for snow, generally KDP will be higher when it's more wet, and KDP will be higher, especially when we're generating those dendrites and plates aloft. And we'll touch on that very, very soon. One challenge for KDP for the winter is that we're looking for teeny tiny little values compared to the summer. So on the left, I have a pretty standard KDP curve. And if you were to look at that, it would be, well, not very exciting. But if you adjust your color map and tune it for highlighting those 0.2 to 0.5 degrees per kilometer range of values compared to like the 3 to 5+ degrees per kilometer. And again, that's how many degrees per kilometer is that the phase shifting. Boy, that's something really jumps out along the North Shore there of Lake Superior. So we need to tune our color maps to be able to highlight those. I have a GR one that I can share. And that's a very important factor with KDP. CC, similarity, uniformity. Pick one, doesn't matter, whatever's going to stick in your brain. So how similar are the horizontal and vertically polarized pulses behaving from pulse to pulse? Generally, it's going to never really be 100. But the more we start to mix in different types of hydrometeors, the more they are regularly shaped, i.e., wet snowflake aggregates. They're kind of wonky looking. CC is going to drop down. So we focus on that. If we have more dry snow, less aggregation, crystal habits that are much more uniform, CC is going to be very high. If we're mixing in different crystal habits, i.e., we're mixing in different types of snowflakes, if they're aggregating up, if they're starting to melt a little bit, we just get a whole lot more stuff going on. So it's just hard to be this more. It's hard for the pulse to remain fairly well the same or acting the same, and that's why CC does drop out. Not all mixes are the same CC wise. CC will be lowest when each type has a near equal contribution. So here's some Petri dishes, I guess, I don't know, of hydrometeors. We see on the left that we're going to have a lot higher CC because for the most part, the signal's being dominated by snow. On the right, we're going to have a lower CC, even though they're both mixes. There's pretty much more equal contributions in the signal from rain versus snow, and thus we see a lower CC. So how reduced that CC is can tell you somewhat the proportions of how much mixing there is or isn't of the hydrometeor types. All right, here's finally some radar data. I'm sorry we had to get through all that, but I think it's hopefully important. So this is from Northwest Wisconsin, I don't know, a year or two ago. And one of our lead forecasters, Jonathan Wolf, who IE is the designer behind all the awesome tools that all you guys use out there in the field, forecast points and all that good stuff. Shameless plug for Jonathan. The CC trend really gives you insight into the proportions of how much one hydrometer type is contributing to the other. So we see initially a mix across Northwest Wisconsin, and we oddly kind of see this backing up at this CC, and we see that the snow is starting to take over aloft. We're starting to erode our at least some type of melting layer aloft, and it can give us insights into, again, what is going to happen at the surface. So I thought, this is one of my favorite loops of just, in a relatively short amount of time. I mean, that's really not too many volume scans through this loop. We see this erosion of this melting aloft into pretty much just all snow. And so I wonder if that's going to have impacts there on the Hayward Taff, or if that's going to have impacts for what's going to be happening on US Highway 53 across Wisconsin. So again, CC gives you, especially the trend can give you that insight into how much diversity you have within the hydrometeor types, or if we're starting to become a lot more uniform. So I might have gone too fast. I get a little excited about this stuff. So are there any questions? All right, let's go to something more fun. So, alrighty, signatures. We're going to start with the bright band. You'd be like, the bright band? We know what the bright band is. Well, we'll do bright band 201. We'll do sophomore level bright band. So we'll add a little bit more tinge of complexity as to what exactly you are seeing. Then we'll talk about prolific ice crystal growth aloft and aggregation, which up here in Duluth, Minnesota, we haven't had much. It's completely bare ground outside right now, which is very sad. Then we'll do the refreeze signal signature, and we'll even throw in just a dash of velocity signatures as well. So bright banding, thank you, Professor Reinhardt from Radar for Meteorologists. Well, the bright band, we all see it. We're all fairly familiar with it, but we'll just touch a little bit more on why it is you're seeing what you're seeing. And some of it has to do with terminal velocity. So obviously we know that the reflectivity for ice is a lot less than it is for liquid for the same diameter. That's the dielectric constant, if you remember back to the radar equation. So above the melting layer, snow has a relatively low terminal velocity. It's just kind of hanging out, floating down. As the snowflake enters the melting layer, it starts to melt from the outside in and begins to look like a large raindrop. So that is what gives us that 5 to 15 dB jump. But what gives us our reduction in reflectivity? Well, that's largely based on terminal velocity. So as the snowflake continues to melt, its size decreases, it becomes, well, a raindrop, and it starts to step on the gas. It starts to speed up its terminal velocity. And that increase in terminal velocity reduces how many targets are being sampled. And that leads to about, well, a 5 to 10 dB reduction in Z. So that's why you see your Z dropping out as you are exiting the melting layer. So as you're entering the melting layer, it's all about kind of the dielectric constant, how shiny that hydrometeor is. And when you're exiting the bright band, that reflectivity drop is all because it's starting to move a lot faster. It's as it's become a liquid. Where's the bright band? Well, I think we can all see it here. So, all right, let's go to prolific dendritic growth aloft. So this is in everything that we show here is a GR color curve that has been tuned to show those KDP values, especially around 0.2 to 0.5, for really care for the winter for its relation to prolific ice crystal growth aloft. It's something I can share out. If you don't like these colors, come up with your own, whatever's going to highlight that kind of zone a lot more to make it stand out. This is from our blizzard last winter when Duluth at the end of the year broke the record for the most snow in a season. Now we're on track to have the least amount of snow in a season. So we haven't been able to play with this a whole lot this year, but this is essentially a fire hose, partially coming off the lake, but I'll show you from a Chanhassen example. It's not just a lake effect thing, of a fire hose of snow arriving in the North Shore. So we're going to focus on just this sea of reflectivity. Yeah, there's a lot of reflectivity everywhere. Okay, but there's a very distinct zone of a lot higher KDP north of Castle Danger, south of Silver Bay, and the North Shore. Well, what is that? Well, that's a zone of enhanced ice crystal growth aloft. So why is KDP higher there? Well, it's running into a lot of stuff. So stuff for KDP. So we're running into just a lot of targets in the dendritic growth zone. And because of that, we're causing a shift in the emitted wave, which is giving us a higher KDP. Let's also remember the way that those snowflakes initially are. They're kind of fluttering and they're more kind of flat. So their horizontal axis is a lot bigger than their vertical axis. And remember that horizontal axis, if that's larger, that contributes to a lot more positive phase shifting and higher KDP. Now it's not 6, 7, 8 as it is in the summer. It's 0.2, 0.3, 0.4, 0.5 degrees per kilometer. So because we're running into a lot of stuff and a lot of stuff that's kind of being generated as it's initially generated, it's fluttering in the horizontal, we're getting KDP that's relatively higher there. Again, relatively higher. You got to have your color maps tuned to be able to see this. Otherwise, it's just going to look like all red or pink or magenta. And so we can see this zone of enhanced ice crystal growth aloft. And why do we care about that? Because that leads to high snowfall rates and impacts at the surface. So again, we talked about that. One thing that we'll show in the next example is as we generate these dendrites, and if we start to aggregate up, they start to clump. Well, what does that do? Well, it in the end starts to take away how many particles there are. They're more bigger particles, but the overall concentration of them is a lot lower. So actually, our KDP will drop to the surface. We'll get to you, Chanhassen, first, but we'll give, gotta remember our complex terrain friends. So a mountain convective snow, same stuff applies everywhere, although one thing they found, and this is from Schramm et al. 2015, this is from the chill radar, and it is kind of like a RHI quasi-vertical profile. This is reflectivity in the upper left. Upper right is ZDR, and KDP is in the bottom right. So we see this, what is a rather impressive blob of actually much higher KDP in these in convective snow showers, especially shown in their study area in the mountains. So in this presence of this convective instability, a lot's happening. We're growing snowflakes by riming, by aggregation, by vapor deposition. They're all contributing to this growth. And what's happened is that we're making aggregates a lot faster. And so our ZDR actually doesn't get that high aloft. And that's because with that convective instability, we're just growing so much stuff so fast and it's clumping together a lot faster. It's not clumping as it's falling. It's more or less clumping as it's forming. Yet we still get that very large KDP enhancement aloft with that initial generation of all those ice crystals. So big thing is to key on is the KDP aloft for the ice crystal growth. If you're not seeing that higher ZDR aloft, we see a little bit of higher ZDR aloft that decreases towards the surface. Well, it might just be because you're aggregating and deposition and riming, and we're getting aggregates a lot faster. We're going to rewind the clock to last week from Ash Wednesday and Valentine's Day snow. It finally snowed, amazingly, in the Twin Cities in Minnesota. It actually snowed, which is not been a too common of occurrence. So a very small taste of the mesoanalysis, and then there's the snowfall. I mean, these aren't gargantuan totals, but it's a massive percentage of the seasonal total for the Twin Cities. Up in the upper right here is our mid-level lapse rates, max 2 to 6. So steep mid-level lapse rates. There's the Chanhassen sounding, deep, fairly steep lapse rates. Obviously the dendritic growth zone isn't super deep because of the instability, but that is somewhat augmented instead by the instability. So we're set up to dump some snow on Ash Wednesday and Valentine's Day. So here's one example, and I'll show an even better one. So in the upper right is the FGen at 850 millibars. Again, that's a 40-kilometer grid. So we're looking off to the northeast of the Twin Cities to my childhood grandma's cabin stomping grounds of north of Balsam Lake on Bone Lake. And well, there it is, our zone of enhanced KDP and our zone of enhanced ZDR aloft. So we're generating a lot of stuff, a lot of dendrites that are fluttering horizontal axes larger than the vertical axis, tied with higher Z itself, tied with slightly reduced CC just because of the fluttering. And we have this relative zone of, well, enhanced snowfall rates across northwest Wisconsin. And then you can ask yourself, does this zone of FGen, this strong zone of FGen from across southwest Minnesota, arcing, or trying to get into the Twin Cities, is that maybe does it extend a little bit further to the northeast? So you can kind of, start to question, put all the pieces together and, okay, is this, 40-kilometer wrap analysis capturing potential for the FGen as much as the radar suggesting? Are we maybe having a stronger FGen band that's a little bit further to the northeast than what the mesoanalysis would say? I don't know in this case, but it's a question at least to ask yourself based on the radar trends. So we'll switch off to same event, looking out to the west of the Twin Cities. We're going to go from the 1.8 scan down to the 0.5 scan. And okay, so we're essentially we're well, east of Hutchinson is where we're looking. So the Minneapolis suburbs, and we're looking aloft. Okay, we're going to look essentially over Hutchinson. And we see this zone of higher KDP aloft and this zone of a slightly enhanced KDP or ZDR aloft. We go down, still there, still got this zone of higher KDP, higher ZDR at 1.3. We go down, and notice how we go to 0.5, they start to fade. So we're having our zone of higher KDP, zone of higher ZDR aloft, where we're getting that prolific ice growth, those fluttering dendrites, more horizontally axis than a vertical axis, generating a lot of stuff. And then as they head towards the surface, they are starting to aggregate, leading to high snowfall rates. As they aggregate, they look a lot more spherical to the radar. So that's why ZDRs drop into the surface. And because there's less of a particle concentration, the KDP starts to decrease towards the surface. And we can see this in cross-section around Hutchinson as well. So we see our higher KDP aloft, our higher ZDR aloft, where we're generating those dendrites that are fluttering. And then we see those two values decrease towards the surface because of aggregation. The aggregate looks more spherical to the radar, and there's less of them because we get clumping. And so that the KDP is decreasing towards the surface. All signals of high snowfall rates. And that's what we saw in the Twin Cities. Picked up a real quick, 4 to 6 plus inches of snow in some spots. Very welcome for the World Cup or the main major cross-country ski race that was in the Twin Cities this past weekend. So, okay. Any questions on any of that? All right, let's go into something slightly more complex. So reef-free signature. And so Kumjin and Tobin are the big ones here in their papers. And what they noticed is, where's ZDR? We're going to focus in on this upper right, square here. And what they noticed is a lot of cases, especially where we're getting refreezing. So thinking of fully melted hydrometeors coming out of a melting layer, they refreeze. There's an increase in ZDR. Why is that? It's kind of, we'll dive into that, but it was something that they noticed. There's also a very small increase in KDP, but for the most part, we're going to focus in on is ZDR. So what they saw is that the enhancement of ZDR occurs very near the coldest sounding observed temperature. So you get this strong enough sub-freezing layer that's able to completely refreeze a fully melted hydrometeor, and you're getting a ZDR enhancement in there. At the same time, the reflectivity is decreasing, which is interesting. So, and that ZDR enhancement is accompanied by a little bit of a decrease in CC, which is a little bit below KDP. But the main thing that we're going to focus in on is ZDR. Why are we getting this, especially this enhanced ZDR in the refreeze layer? Which is below the melting layer for hydrometers that are fully melted. So here's what it looks like. So I'll show several, and I think I spelled Kunjin's name wrong, so my apologies. But all right, so there's our ring of melting aloft, pretty typical of what we see. In this case, notice how this ring of melting in ZDR in the upper right, and here's CC. So CC is reduced because we're getting melting, different hydrometeors, a lot of stuff going on that's not well correlated from pulse to pulse. Things are melting, so they're more horizontally aligned. And we got bright banding, all pretty standard stuff. But we're seeing then is within the melting layer, or at least like encapsulated by it on our plane view of radar, is we're getting rings of higher ZDR closer to the radar where we're getting a refreeze. Of note also in this case, you see how the melting layer is a little bit shunted to the southeast. Basically says there's more cold air to the northwest, the warmer air is off to the southeast. Again, very similar. Melting layer in ZDR in the upper right, CC in the lower right. And we see then this signature of this kind of reemergence of higher ZDR closer to the ground associated with refreezing. Same thing here, probably even more stark. Melting in the high ZDR right here. Everything's fully melted, so it's just more of a spherical raindrop. So ZDR drops to closer to zero, and then as it's refreezing, the ZDR starts to pick back up again. So why is that happening? Well, there's a few things that are going on and a little bit of unknown. So one thing is that they conjecture is this preferential freezing of small drops. So the small drops are freezing first. So they are contributing, well, they become ice. Ice is not as reflective as water, liquid water. So that's why you're getting that reduction in reflectivity. But at the same time, because what's left is that is more oblate shapes are left from the larger drops, so that the larger ZDR values are left. And remember that ZDR is biased, especially towards the larger targets. So as the smaller drops are refreezing first, they're turning to ice, thus the reflectivity is dropping. They're also that sample that were with the radar, and what's left, especially after that refreeze, is the larger drops that are more oblate. And so we kind of had this coincident increase in ZDR with the refreeze. Now we're going to hopefully not become too mind-bending as we think about ice. So what they found, again, so where we have we're going to first focus on complete melting. Okay, we have a strong warm layer aloft. We completely melt any snowflakes that are coming into the melting layer, so that they're fully melted. These smaller drops preferentially freeze first, so you're left with bigger drops. And the bigger drops have a higher ZDR. But that doesn't explain all of the ZDR increase. Another thing that they do talk about is that they start to form an ice shell, and we get kind of this oblate ice shell with a little bit of slush in the middle, and that also leads to higher ZDR. Well, what they also found is that for partially melted snowflakes that refreeze back into sleet, there is no ZDR enhancement. Okay, so how is that useful? Well, it gives you insight into the conceptual model of the thermodynamic processes, the microphysical processes that are going on in regards to sleet refreeze. So if we're getting sleet at the surface, and all right, so we'll just jump to this one. So if we're getting sleet at the surface and we're seeing this ZDR enhancement, this refreeze signature, we know that, well, we got fully melted particles that are likely potentially supercooled at some point. So that might matter for aviation and the CWSUs and AWC. And if we're getting sleet at the surface, which doesn't have that ZDR enhancement, that refreeze signature, kind of within the melting layer, at least encircled by it, then we know that, okay, we have hydrometeors that are only partially melted. So we don't have as much of a supercooled presence, i.e. Threat for aviation there, although not completely zero. So let's apply this. So we're going to take a prolific sleet event from Wilmington, Ohio, on February 3rd and 4th of 2022. This is on the left, it's a progression of, I don't know, like 4 or 5 soundings, which I thought is pretty cool that they're launching at like 15, 18, and 6Z. I like it. Good use of those balloons. We can see a very strong melting layer aloft with a very strong refreeze layer. They're fairly proportional, so we're favoring the production of sleet. On the right is just kind of towards the end of the event, because it shows the sleet accumulations on the order of 2 to 3 inches of sleet, which is probably a problem across Cincinnati and into Wilmington, Ohio. But we're going to first start out, we're going to kind of pair our soundings with radar. And this first one is 12Z on the 3rd. And the main thing we want to look at here is actually the velocity pattern. So not dual pole, sorry, but I thought it was pretty cool. Focus on our wind pattern and our velocity pattern. I think someone might have raised their hands. Sleet Fest. Yes, Sleet Fest from Wilmington, Ohio. So once the velocity pattern has it has a couple patterns to it. So down low, we have winds from the northeast. So, well, what's that picking up? That's picking up our very shallow, low-level cold air advection and northeasterly flow. Above that, we have southwesterly flow aloft. So that's our large warm air advection supporting that warm nose and that strong mid-level jet and southwest flow aloft. So we're able to see the spatial coverage, and then if we would go up in height, we could somewhat potentially judge the depth of the cold air advection of the refreeze layer. We get some sense of its depth. And then we can just see that we have this alternating pattern of advection patterns and melting and refreezing simply from the velocity itself. So the good old fashioned, and this is from RAC or DLOC, if it was DLOC. I went to DLOC. That shows you where I am. I'm getting to be the older guy. So good old fashioned velocity patterns. When's the last time you looked or thought about these? Do you even remember them anymore? So that S-shaped pattern being our veering, our warmer advection pattern, our backward S-shape being our counterclockwise, our backing winds, our cold air advection with height. And here's from Wilmington, the same event, you go high enough and oofta. A lot going on here. So, but we can still see that northeasterly flow. We can maybe try to get potentially some sense of a depth to it, and then we see a lot of stuff going on aloft as we're getting minor backing and veering patterns aloft. You know, all encased within the broader southwest flow with the jet. So, but that has nothing to do too much with sleet. So we're going to again go from higher elevation to lower elevation for Wilmington. We'll start at the 4-degree elevation. Pretty standard here. Circular melting layer showing up in all the moments. All right, we go down. Becomes a little bit more wonky, but for the most part, we can see our melting layer fairly distinctly. And our ZDR is, actually, for the most part, decreasing towards the surface. So we need to ask ourselves then, so we probably don't have a deep enough sub-freezing layer near the surface to refreeze fully melted hydrometeors back into sleet, because we really aren't seeing that increase in ZDR again towards the surface. What we are seeing is a heck of a lot of melting aloft with ZDR. That's, for the most part, decreasing or steady, relatively small near zero as we approach the surface. So we probably have a lot of melted raindrops. Now, are they partially melting back into sleet? Probably not, but just because CC is not overly reduced, so things are for the most part uniform. So what was going on at this point? Well, it wasn't sleet fest yet. It was freezing rain still at Wilmington. And that's really because we had that lack of a refreeze signature in general. ZDR was nearly the same or slightly lower inside our melting layer. So for now, we have a lot of just freezing rain falling at Wilmington. We kind of see this kind of, again, the shunted pattern off to the northwest in our melting layer. It's a little bit closer, a little bit compressed compared to the southeast. So that just tells us that, hey, look, the cold air is a lot closer to the northwest, and the melting and the warm air is a lot stronger and broader across to the southeast of Wilmington. Now we're going to go to 18Z. And we have about as classic of a freezing rain sounding as you can get. We're going to focus on the 1.3 and the 0.5 elevations. And the emoji is telling you to notice ZDR. So ZDR is, we have our circular melting layer. And then we have this kind of blossoming relatively of ZDR as we're getting closer to the ground. So that might be the refreeze layer. So let's take a deeper dive into that. So again, aloft, we have this, we can see our melting layer in CC and ZDR and KDP, even for the most part in reflectivity. But we're also starting to see that kind of ZDR pick back up again closer to the RDA near Wilmington. If we go down to the 0.5, we see it even larger, a more blossom ZDR. So we are melting in our, for the most part, circle. We get full melting because we have a lot of spherical drops that are fully melted. So that's where we kind of get this darker blue ring. And then ZDR starting to crop back up again. And that's a signal of refreeze. And that's as the smaller particles are freezing faster. We're getting kind of these oblate ice shapes that have this slush core, and so that's leading to this increase in ZDR. So we can have fairly high confidence. Obviously, look out the window and it's leading, but if you didn't have that advantage of looking out the window, we can see that definitely the conceptual model of fully melted hydrometeors refreezing to sleet is ongoing. It's fairly prolific. It's fairly large in spatial coverage. And what do we get? The good old UP on the METAR. So most likely sleeting in Wilmington. The last sounding we'll investigate is then 0Z on the 4th as our CC line of where is it a mix versus all snow is marching towards Wilmington. And by the time they've launched that 0Z sounding, pretty much the entire sounding was sub-freezing, which leads to some pretty crazy looking dual pole signatures aloft. I don't know, an angel, a butterfly, something in ZDR there at 1.8. Really kind of this wonky pattern to it. So, but we can break it down. So we have our angelic butterfly, whatever pattern in ZDR here that's higher. Okay, so that's where there's melting. The challenge is here is that we have a complex pattern because the RDA is basically now all enveloped in the sub-freezing air, and the beam is shooting out, and it's going through where it's refrozen. It's going through snow, then it's going into refrozen sleet, and then as we go a little higher, a little further out, then it's going into just fully melted hydrometeors. We're going a little further out, a little higher up, and we're going now into partially melted hydrometeors. So we got a heck of a lot going on. And because it's not like greatly centered over the radar, we get a pretty crazy looking shape to it. But we can break this down. So we know that colder air is marching in from the northwest as our CC line has approached us. Uniform CC, pretty low ZDR, low KDP. It's probably just snow. Go directly to the southeast of the radar. Now we pick up this little enhancement of ZDR that's encapsulated by all of the melting layer. So that's our refreeze. Where we get into the darker blue, where ZDR is closer to 0. So that's our more spherical, fully melted hydrometeors. And then where we get out a little bit further, we get those partially melted hydrometeors that are a little bit more horizontally shaped. So Joey Pica out of SBC has a great video that talks about this, that you get these complex patterns as you're moving, as your beam is kind of moving through a whole lot of completely frozen snow setup to, different from a refreeze to fully melted to partially melted. You get these crazy kind of patterns. And very similar, kind of as we see here down at the 0.5, we definitely see our refreeze signature between Wilmington and Hillsborough, encapsulated by the larger melting layer as well. So, all righty. So that was 48 minutes. I got about 5 more minutes. Any questions on this or Wilmington? If you have any comments on it, feel free. Just chime in. Don't even have to raise your hand. All right, so what's the takeaway? Well, dual pol is great. Use it. Okay, let's maybe something a little bit better than that. How about that? So admittedly, dual pol, it does not always have the most accessible concepts, at least initially. You got to put a little effort into it. But if we break it apart into physically what things represent, then you can kind of put all the pieces together. And hey, remember, dual pol, it's one of your most rapidly updating data sets in your winter mesoanalysis toolbox that can provide you direct insight into thermodynamic, hydrometeor, microphysical processes. Ask yourself, do my winter observing procedures, they probably have reflectivity. That's probably a given. Maybe they have CC. Hey, do they have ZDR? Do they have KDP? Are you overlaying MPing reports? What data are you leaving on the side that can be incorporated into your procedures? Are your color maps tuned to be able to see these things, especially for KDP? Additional resources, for me, it's probably been, I don't know, 16 years since I took Winter Walk. So, hey, go back, revisit it. They got updated content. I know Andy Wood's done a lot of great stuff and updating it for dual pol signatures. So, Sarah Graffiti, Andy Wood, big plug for them, and Winter Walk. Go back, take a look at it. The SPC OU lecture series has outstanding short dual pol videos by Joey Pica. They are not only for summer convective processes, but also there's like 4 or 5 great ones on winter. They're like 10, 11 minutes long. And he probably explains it better than I do. But I'm going to put the finishing touches on an updated winter dual pol applications guide. A few things that I want to update, having made all this presentation. And then pull up some radar, play around, especially in this boring winter where there's not much to investigate, at least not yet. We got a ways to go still to be out of it. Pull it up, GR, play around with it, see what your GR setups are. There's some great papers. Yes, we still read papers. They are worth your time. Here's some great ones that I used that are, I think, pretty accessible, great operational takeaways. And I think that's it. Take any questions, any comments. But for the most part, I just wanted to take some time to kind of go through, holistically review of dual pol and how we relate that to winter and how we can bring a little bit, how we can leverage that data to squeeze out information that really not a whole lot else is going to give you that, right? So hopefully it gives you a little more confidence in using some of these things. I mean, I'm no way an expert in some of these things. Sometimes it's a little head scratching to me and I got to think about it a little bit. But if we can break it down, see how the pieces fit together, it's going to help you out in the winter. It's going to help you out in the summer. All right. Right. So break it down, break dual pol down into those simple things of which each piece means. And I think we'll get somewhere. So I'm done talking unless there's any questions.
Thanks, Patrick. That was an excellent foundational overview of Winter Dual-Pol. Looks like Rebecca has a question or comment in there. Just basically saying the same thing.
Yep. I'm switching screens now. I can see it. Yeah. Exactly. So something that we've done, we did last year is that we also hosted just radar clinics that more like convective based, which go back to the basics, right? And I know that WDTD is making that effort as well, and bringing back some of those availability to go through some of the more foundational things, because for a lot of folks, I mean, you go through RAC or DLAC and you've stared at some of this data for so long that you start to forget about, well, what does ZDR really mean? And then when you try to apply it to, I don't know, refreeze or ZDR arcs, you name it, it's a little bit of a struggle. So, yeah. Yes, Aaron Johnson. Thank you, Aaron. From a SWIP standpoint, TWIP, so the Convective Warning Improvement Team, formerly the Tornado Warning Improvement Team, several modules on dual pol applications as related to convection. Makes me think at some point we probably should do something related to winter, although it's probably not in the purview of the SWIP team. We'll have to figure that out. But yeah, go through those. I highly recommend them. I highly recommend going through Winter Walk, some of their, target. You don't have to do the whole thing. Just go pick a module or two. Go watch Joey Pica's, just Google SPC OU lecture series, dual pol. Go to the dual pol section. Take 10 minutes on a quiet shift and learn something. He does a great job with it. So anything else? I'll happily share out the slides. I'll share out the guide. I'm not I didn't come up with all this stuff. I mean, it's stolen from papers and other SUs and RAC and WAC. So just try to condense it all together for you folks. So